Understanding Materials Lecture 5 by Lee Burton. We have learned about making band diagrams. Now let's see how to interpret them. Firstly, we can see if a material has a band gap. It is possible to push electrons across this region by giving them an energy greater than the gap. But electrons can never reside within this energy range. Remember we said states below 0 eV on the y-axis are full, and states above 0 eV on the y-axis are empty. Let's imagine the bands are composed of discrete states again for now. Once an electron is pushed across the gap, it is free to move through the conduction band. Like a kid moved from a crowded room to an empty hallway, whereas electrons in the full valence band can't move. If there is no gap, for example, a gap smaller than 0.2 electron volts, even the energy of room temperature is enough for electrons to cross to empty states. These materials are called conductors or metals, and are characterized by easy conduction of electrons. If the gap is about 3 electron volts or more, it's an insulator. The energy gap in these materials is typically too big to push electrons across, and so can be trusted to not conduct. If the gap is about 2 electron volts or less, it's a semiconductor. So called because they are in between conductors and insulators. They can conduct, but not as easily as metals, hence semiconductor. We see silicon is a semiconductor from its gap. While electrons can be freed in metals with heat, even just at room temperature, electrons in semiconductors need more to free them. For example, with applied voltage in the form of electricity. This is exactly why semiconductors are used in electronics, by the way. We are familiar with all three of these material types. In modern electronics, for example, metals are used to deliver electricity. Insulators are used to protect you from the electricity, and semiconductors are used to process and store information using that electricity. It is also possible for light to give this energy. Photons are the messenger particle of the electromagnetic force, after all. Let's return to the discrete state representation of the band diagram to see the process of excitation by light. Firstly, light arrives to the material as photons. A photon's energy depends on its wavelength, and a broad range of wavelengths reaches from the sun. A photon with the right energy can be absorbed by an electron, elevating it to the empty states above the gap. Excitation begins first at the location with the smallest gap, so the energy of light absorbed is set by the band gap, which is why separate materials have distinct colors, by the way. Photons only push electrons to bands with the same K point, which on a band diagram appears as a vertical transition, which means we can also see if a band gap is direct or indirect. For silicon, we can see all of the direct gaps are large, and the smallest gap requires a horizontal shift, meaning that the smallest possible gap is indirect. So now we know how to see that silicon is an indirect bandgap semiconductor, just from a glance at the band diagram. And these features are true for any material. In Lecture 6 we will go even further into seeing what more can be inferred from a band diagram. Understanding materials, end of Lecture 5.